Hello everybody. Hi guys. Welcome back to another video of Elise's Astronomy Crash Course. This episode will be centered around the inner solar system and everything inside the asteroid belt. So I'll be going through that. I have some notes. Here are some notes right next to me that I'll be referencing because the planets in the solar system are not my area of expertise per se. I want to say a couple notes before I begin. Those include that I am not taking customs at the moment because I've been super busy and I had some not safe for work requests, so I'm putting that on permanent hold until further notice because I had some people ask me for lingerie role plays and like wife cheating on other people role plays and just some stuff including sucking on things that were not appropriate, and I don't want to continue getting emails like that. So unfortunately, I am not going to take customs at the moment. So just to let you know about that, I am so sorry, but I don't feel comfortable anymore due to those experiences. And another thing is I'll be uploading less frequently. I'm so sorry, but life has been really busy right now. And so, yeah. But I'm here right now, and the series will continue, and so here's our next episode. So let's get into it. So we have the inner solar system, and we talked about the sun in our last episode, which is actually a star. And then we have 4 major planets in the inner solar system. There's the inner and the outer solar system, and they're separated by this region called the asteroid belt, which I'm sure most of you have heard about in school. It's literally just a strip of asteroids that go in orbit around the sun in a region called the asteroid belt. And then we have 4 what we call terrestrial planets, which include Mercury, Venus, Earth, and Mars. And the characteristics, of these terrestrial planets are that they are rocky, they are very, very dense, so they have the composition of mostly stone or rock, and Earth's is 5.5 grams per centimeter cubed, so it's pretty dense, I have to say. And Mercury's, I believe, is 5.4 grams per centimeter cubed, and for reference, air is 0.001 grams per centimeter cubed, and I believe water is 1 gram per centimeter cubed as well. So that's generally the reference point. So it's it's dense. These also have metallic cores, and they vary in size, and they have mantles too, but they generally have a silicate mantle, and then they have a metallic core made of mostly nickel or iron. So those vary in size as well, and that metallicity can contribute to magnetic fields, and I'll explain a little bit more about how those come about, especially when we get to the outer solar system, but that's it for now. And so I think Venus, Earth, and Mars all have atmospheres, but they vary in thickness. So Earth's is kind of like an intermediate atmosphere in terms of thickness. Venus has the thickest of the terrestrial planets, and Mars has a very, very thin atmosphere. I think it's 100 times less than Earth's, but Venus is quite thick. And so now I'm going to explain like a little bit about the planets and stuff like that. The first thing I want to talk about, and this is more a physics principle, but I'm sure most of you have heard, Mercury is in retrograde. Oh my God, my life is so terrible. I can't get up in the morning. Oh, it must be because Mercury's in retrograde. I got fired. Oh, it's because Mercury's in retrograde. I missed the train. It's because Mercury's in retrograde. because Mercury is in retrograde, and that's an astrological concept. It's not founded in astronomy, but people like to joke about that because what that essentially means is Mercury is the closest planet to the sun, and it has a resonance period, and resonance is basically like this this ratio of orbit to spin that it gets stuck in, and Mercury's is 2 to 3. So it really likes those integer numbers. Earth tends to like, sorry, not Earth, the world tends to like integer numbers when it comes to orbits and ratios and stuff like that. We'll get into Jupiter and parts of the asteroid belt that it pulls out and leaves rings in that. But yeah, so Mercury in retrograde is kind of the idea that if you're passing a car on the highway, and let's say this is the car going kind of like, let's say 50 miles per hour, and you're going at 70 miles per hour, and maybe you start in different places, and you're kind of going, and you're going, and you're going, and eventually if you're faster than it, you're going to pass it. And from your point of view, it looks like that car is going backwards, although you're just going faster. And that's the idea of retrograde, is that Earth is on the outside and Mercury is on the inside. And temporarily, as we're passing Mercury, it looks like Mercury is going backwards, just for a little bit. And that's the idea of retrograde, is then when we see a Mercury in the sky and we track it, it looks like it's going forward, and then for a moment it looks like it's going backwards. And then when we pass Mercury, so we pass Mercury, like when we're going by it, it looks like it's going backwards. And then as we finally pass it, it goes forwards again. So it kind of makes a zigzag motion like Harry Potter's scar, because we're going past it. So that's the first cool thing about Mercury, is it has a 2 to 3 resonance. So I think it's for every 2 orbits, it spins 3 times, basically. And it really likes that resonance as well. So that's a little bit about Mercury. And Mercury is the closest planet to the sun. Another cool thing about it is it has a giant iron core. So it's got an iron nickel core, and it has a tiny mantle. And we think this is because probably a similar sized body that was mostly metallic hit it. And then those cores merged together into a huge core. And then it flung out a bunch of rock. And some of the rock escaped with escape velocity and never came back. And some of the rock that was slower just kind of compiled back onto it, and that's why it has such a huge core compared to the mantle, because on Earth we have not a tiny core, but we have a medium-sized core and a bigger mantle for sure. So that's why we think Mercury has that deviation, is because it just combined cores. And so that's Mercury. And then Venus is interesting. This is a broad overview, by the way. I'll get into this later. But talking about cores anyway, Venus has a core similar to Earth. It's mostly iron. It has a rock silicate mantle. And Venus, we think, was originally much like Earth in terms of atmosphere and climate. It may have had water at some point too. Water, or a methane ocean, which is CH4 in a chemical formula. But at some point, what happened to Venus and why it's so hot, actually Venus is called the morning or evening star in the sky, and I went over this in the first video when I did a solar system overview. But Venus originally was thought to be a star because it has such a thick cloud layer that it reflects most of the sunlight. And this means we can't actually see surface details very well on Venus. We kind of have to use radio to get past that cloud layer and see what the surface of Venus is actually like, or we have to send satellites down onto Venus and map out that surface. But Venus is a really cool planet because it's so hellish, and it's unlike anything we've really seen in the solar system or in other solar systems. It's kind of a rare occurrence. And what we think happened was there might have been water on Venus at some point, but it basically, water kind of compacts carbon dioxide into rock and it compacts it into the water, and it slowly over time sucks carbon out of the atmosphere over millions of years and kind of deposits it in rock under the ocean. And carbon dating, which is it's a way we use on Earth to track Earth's history and what happened to the magnetic field lines over time, and other cool things. But carbon dating is basically tracking the amount of carbon in the rock over time, and then figuring out dates based on that. And for Venus, there was a lot of carbon, we think, in the lake, ocean, rock area on the ground. And then what happened was something where we got a positive feedback loop. So it started evaporating, Venus started heating up. It is closer to the sun than Earth, so it's still in this thing we call the Goldilocks zone where life could exist, and we have liquid water, which is why we think there was an ocean on Venus. But it probably was too hot where it started evaporating, and then it evaporated at such a rate that it basically boiled all the oceans away and made a cloud layer. And that cloud layer acted as like a greenhouse where it trapped all the infrared light, all the heat, and infrared light is basically heat. It trapped all the heat and warmed the planet so that it kept boiling away all the oceans until there was nothing to boil. And then it started sucking all the carbon out of the rock. Essentially, it heated the rock to such a point that it sublimated and released gas, and then that carbon got stuck in the atmosphere, and greenhouse gases trap heat, and then it just became this super hellish place with like a super dry, super, super hot ground and this huge thick cloud layer where you can't even see it. It's just huge. It's super thick, and we think there may be acids up there and nasty stuff. So Venus is not a place you would want to go. But Venus is really cool to study because it is similar in mass and volume and composition to Earth. So it's kind of like the hellish sister, I guess you could say. And then we have the moon, which is technically not a planet. It's a moon, but our moon is an interesting place for sure, because I'm going to go into the Earth and moon a little bit later in this video, but essentially what happened is the core of the moon is in fact an iron core, but it's slightly off-center. So when you think of core, you think, well, metal is really dense, so if I put a metal ball in water, it's going to sink, right? That's kind of what happens to most of the metal in planets, is that it's so dense, it just sinks right to the center of everything, and then it just attracts everything else to it. So it's kind of got like the most dense in the center to the least dense on the outside. That's why we have the atmosphere on the outside and the core is iron. But the moon is weird because it's got a tiny little core, but it's not in the center. And then you think, well, metal's really, really dense and it's heavy and has a lot of gravity. So why is it off center? That's weird. Like, there has to be a force pulling it so that it's not in the center, right? And yeah, that's basically what it is. Because we have a moon and Earth is a really, really big mass that has a better density, a heavier density than the moon, tidal forces essentially are pulling the center towards us. So we're pulling on the mass just as it's pulling on us, which is actually why we have tides. The moon is pulling on the water on Earth because it's easier to move water than it is to move solid rock. So the water gets pulled towards the moon, but also over time and due to angular momentum, which I'll talk about later, the core is being pulled towards us, and that's why it's slightly off center. It's being pulled towards the close side of the moon, not the far side. So it's closer to us than farther away, which is interesting. And so that's the moon. And then for Mars, it's not a tiny core, it's not huge, it's a pretty average core for Mars. So yeah. And now I'm going to talk about, what do I want to talk about? See, I'm not really structured for this video, but I could talk about, what do I want to do next? Maybe we should talk about how planets form a little bit. That would be good. I'm so sorry, I don't really have a structure for this video, but I'm gonna like try to add a bunch of information for you guys and try to make it as structured as I can. So I hope you're having fun so far. But basically the planet stages are, first we have something called accretion. So when stars form, it's basically made from a giant cloud of gas that collapses under its own weight, and then forms fusion, and that's how you get a star. It's a big enough mass, it's a little bit bigger than Jupiter, where fusion can happen. And so that gas is made by a disk of material, and that essentially can form not only stars but also planets. And so this is called planet accretion, where essentially a bunch of mass is condensed together. And these can make, like, gas can form little bits of dust that sort of stick together over time, over millions of years, and then they kind of just coalesce into a giant ball. And sometimes if you look into the far solar system, you'll see that sometimes these bodies out there, some of them are comets, but they're not really balls of material. They're actually more just like loosely clumped rocks that are held together by their own gravity. It's like, what's something next to me that I can show you? Well, it's like, let's just say that like these are all clumps of rock, and instead of like these clumps forming together and making something bigger like this, instead of all of these three clumping and forming this solid body, they all just kind of stick together like this and float around. But they don't actually like mesh together to make something else. They kind of just stick like and move around. And so that's one thing they can do, but most of the time they do clump together to make the big thing if they have enough mass. And so sometimes you make asteroids and stuff like that that are weirdly shaped from that sticking togetherness, but sometimes you get planets if it gets a big enough mass. And depending how close to that star, that protostar we call it, the newly formed star, depending on how close or far away it is, you get different properties. For instance, all the dense things are going to be like pulled towards the star, so those rocks that form that dust versus the gas that is kind of blown away forms these gas giants or ice giants, and that makes things like Jupiter or Saturn that are huge, which I'll get into later. We call those the Jovian planets. And so, yeah. So that's the first stage. And the second thing is when you get a planet that's forming, it's like a crust that forms. So a bunch of dirt on top of each other that just makes a crust. And then we get cratering from all those asteroids that are formed too, that are pulled towards it and that hit it and make huge craters. And that cratering can last for millions of years. And then eventually, as that protostar kind of calms down and things get more spread out, then we get like the cratering slowing down or ending, and then we get these giant basins. And I think they're called Mare, I believe, Mare, no, M-A-R-E, Mare, I believe, on the moon are actually these basins of lava that have cooled. Because if you've got like a core and you have magma underneath from being really hot, because remember when planets form, it's like friction. It gets super, super hot and the gravity condenses it together and it gets really, really heated, and then it just cools over time, basically. And then a crust can form on top of it, but it's still really hot inside. Like Earth is really, really, really hot inside. Yeah, but that crust will form, and then if we get a giant impact, it can basically break through that crust really easy, and then on top this magma will flow up and then bubble and make like a whole basin, essentially. So, yeah, and then the surface is really active. You get tectonic plate movement, which is like earthquakes. the crust kind of fractures and moves around slowly over time because the magma underneath will rise and then cool and sink back down because it's denser, and then rise again and sink back down, called convection. And that convection kind of moves the plates over time. So if this is a convection current, it sinks down and it comes up on top of the plate and kind of shifts the plate over. And that's where we get the movement of the plates. And so yeah, and then we got volcanoes from that, where they kind of like push up on each other and make mountains, and then volcano. And you get magma chambers underneath that area that can pressurize and blow up. And yeah, and then eventually the mantle, which is it's kind of like a caramel texture, taffy texture. It's like, it's liquid that doesn't exactly flow really easy. Kind of like gum pulling it apart. Like, that's the texture of the mantle. And it's all rock. It's all really hot rock. And that will solidify first. That will cool down. And then plates stop moving because there's no more mantle convection. So there's nothing, if it cools, there's nothing pushing it again. So tectonic plates will stop. And then the atmosphere will go away usually. And this is interesting. The core will melt. So instead of being a solid core from pressure, it will melt. And then what kind of happens there is sometimes you get an atmosphere that's gone from, there's more complicated physics behind it, but I won't get into it. Basically, it goes away. And the core cools and it becomes just kind of like a floating rock, basically. Earth is kind of in the like fourth stage of the surface is still active, but we have a cool crust, basically. Let's see. Interesting things about Venus. Venus is super cratered, and it's really hard to observe Venus because it's so close to the sun. Sorry, not Venus. Venus too, but Mercury. I'm really tired. Mercury is really cratered. It's really tiny. It's actually pretty dark on the surface because it's primarily silicate stone, but it's heavily cratered and it whips around the sun super, super fast. And Mercury's orbit kind of precesses back and forth, and it is due to a lot of things, but there are, well, I should get into this in a later video, but gravitational waves can help us kind of determine the precession of Mercury's orbit, because it didn't exactly stick to Newtonian physics, and so we use this thing called general relativity to predict Mercury's precession, which is really cool, and I'll get into that later. The area of research I'm really interested in is radio astronomy. I really like cosmology and radio astronomy, so I like the cosmic microwave background. That is the thing that I think I look at the most and is coolest to me. So black holes and the CMB are really cool to me, but that's kind of a tangent. Yeah, what other things can I say? Venus, for instance, is interesting because, so there's an axis upon which every planet spins. And not only does it orbit around the sun, but it spins too. And its axis is through what it spins. So kind of like if this is the radius and this is the axis, it will spin along that axis in a certain direction. But the tilt of that axis can kind of vary. And for Venus, it spins like that. It spins upside down. So Earth spins at like a 23-degree angle, approximately. But Venus spins like this. And it's really weird. And yeah. It has no moons. So Venus doesn't have any moons. Its surface temperature, I don't remember what it is in Fahrenheit, but it's like 750 Kelvin. It's very hot. I think that would be like 800 something Fahrenheit. But yeah, it's pretty stinking hot. And that's because of that positive feedback loop, greenhouse gas effect. So that's cool. Its mass is slightly less than Earth. I want to say it's 0.8 or 0.9 Earth masses. So yeah, it is pretty close to our planet. Yeah. And then Mars is interesting too. So Mars is a hot spot of study because Mars is just really cool. It's kind of a barren place. Think like the middle of Arizona or New Mexico or the Mojave. Like it's just straight up rock basically. And it kind of looks brownish or reddish because of oxidation on that planet, which I mentioned in the first video. But it makes a rusty color because it is rust on top of layers of a stone called basalt. And so that's Mars. And the cool thing about Mars has two moons actually. It has Phobos and Deimos because Mars was originally the god of war. And Mars is red, and red is, blood. And then they thought, oh, Mars must be war. And Phobos and Deimos are fear and panic, which typically follow the god of war into war. Fear and panic comes after that, which makes sense. And so Phobos and Deimos are interesting because they're irregularly shaped, and they orbit like weird distances from Mars, but closer to Mars than the moon is. The moon is thousands of kilometers away. I think it's a couple hundred. No, it's like, yeah, it's several 100,000 kilometers away. But Phobos and Deimos orbit pretty close to Mars. Comparatively, I think it's like 10,000 and 23,000 kilometers away, respectively, for Phobos and Deimos. Another thing about Mars, it has polar ice caps. So we think that there might have been liquid water on Mars at some point. It is in the Goldilocks zone, actually. But we see these like river deltas that don't have any water in them, but we see the formation, and we think that there might have been water at some point. It also has a tiny atmosphere. It's hardly anything, but that atmosphere is able to deflect very slight amounts of solar radiation and the solar wind, which is great. Yeah. Oh yeah, there's another cool thing about Mars. So Mars has this canyon that is called Valles Marineris. I don't actually know how you pronounce it in Latin, but nobody speaks in Latin, so that's a good thing. But Valles Marineris is huge. It's like a scar across the face of Mars. And it's like 3,000 miles, I think, but it's nothing compared to the Grand Canyon. It's huge. It's enormous. It's the biggest canyon in the entire solar system, as a matter of fact. And it also holds the biggest mountain called Olympus Mons, because Olympus, Mount Olympus, matching with the Greek theme here, Greek and Roman theme. But yeah, Olympus Mons is huge. It's super big. I think it would take you 6 minutes to fall to the bottom, I'm pretty sure, if you jumped off of it. Yeah, it probably also had a magnetosphere at some point, because we see in the crust there are fossils of a magnetosphere, but it's not there. And we're trying to figure out why, but we don't exactly know yet. Yeah, so those are some details. And now I'm going to talk a little bit about the asteroid belt. Again, this is meant to be kind of like a broad overview video, and then I'll talk about asteroids and then talk about a bit about Earth and the Moon and tides and whatnot, and we'll conclude there. But again, I would encourage you, if you really want to learn as much as you can about astronomy and really talk to people who know what they're doing, and not just watch like a 45-minute video about it, I would strongly recommend you watch this series and figure out what's most interesting to you, and then take an introductory astronomy course, and go to a local community college, enroll. It's very inexpensive take a late night class, take an online course, interact with the professors and see what you can learn, because it is really cool. It is the geography of the places outside of our planet. It is equally as important as knowing geography of the Earth, and knowing the geography of where you are and what's out there is really important to know, and knowing where it is that you live. And we live in a huge universe with lots of cool stuff in it. So anyway, tangent, but asteroids. So, like in Star Wars, I'm going to assume you've watched Star Wars. If you have not, I'm so sorry, but you are uncultured. You need to watch it. It is great. Star Trek fans, like, okay, I can get behind that, but Star Wars. Go watch Star Wars. I grew up on Star Wars. I love it. But Star Wars did get some things wrong. And one of the things it got wrong was the density of the asteroid belt. Because when like Hans and Chewie are going through hyperspace and they're like, hit the hyperspace, go to the drive, and they all like zoom on the Millennium Falcon, and it seems like there's a bunch of asteroids, or like they're going through a chase scene and they're going through the asteroids, but it's not that dense. Actually, you're not gonna see an asteroid for 1,000,000 kilometers on average between them, and they're not that big. They're like the biggest ones are like 3 kilometers across, like that you'll find typically, like 1 kilometer, but it's not dense at all. However, if you look at like the huge space of that orbit, it does seem pretty dense when you catalog all of them. But if you're actually there and you're human, it's nothing. You're not going to see them. They're really small. Yeah. Asteroid itself, aster, is the, I forget exactly what it is in what language. I think it's Latin for star. But asteroid is star-like or minor planet. That's generally the definition. And the total mass of all of those asteroids together, not only is it not dense, but it's less than the moon's mass. So it's not that much. And they come in 3 different kinds. They come in stony, carbonaceous, and metallicious, or metallic. You can just say metallic. The largest asteroid that we know, which I believe it's actually a dwarf planet, and a dwarf planet is basically like, well, there are 3 rules for planets. It needs to orbit around the host star, in our case the sun, and it needs to orbit in a way that there's nothing that is of similar size in its pathway. So in that orbit, there can't be something like big or close to the size of it in its orbit, or else it won't have cleared its orbit, is the formal written definition, and it has to be spherical, or roughly spherical. Ceres has the asteroids, so it hasn't cleared its orbit. It's an asteroid belt object. So that's the difference there. And that is why Pluto is not a planet, which I have a whole video lined up for you on why that's not the case, and explaining dwarf planets and all of that. But Pluto is not a planet because it has not cleared its orbit. Yeah, we think that Ceres might have like a subsurface reservoir kind of thing, like a giant area of water, but, well, not water. It's kind of ice. Ice is water, but ices in astronomy are kind of weird. Jupiter has a bunch of ices. Ices can be like methane and other things that aren't water, but we consider them ices. It's interesting. I'll tell you about that later. But we think that it might have enough ice to be more than Earth's oceans, which is pretty significant, actually. So we might find microbes there. We don't know yet. And the next biggest one is called Vesta. And both Ceres and Vesta are named as like sisters of Jupiter, per the Roman mythology. Yeah. And so, yeah. And also another thing is I want to name some other ones, so I'm going to read them off to you, and if you're interested, you can go check. They're all smaller than the moon, by the way. They're really tiny, but Ceres is the biggest. Then Vesta. And then we have Hygeia, Pallas, Juno, Astraea, Hebe, Iris, and Plura. And then Metis. We can't forget about Metis. And so those are different ones that you can check out. A cool thing that I mentioned was Jupiter has a strong influence on the asteroid belt because the asteroid belt is pretty close to Jupiter. It's between Mars and Jupiter, and Jupiter is the next biggest thing in our solar system besides the sun. It's big. It was very close to becoming something called a brown dwarf, which is like not exactly what it sounds like, but it's basically like a tiny star. And so it almost got a type of very low fusion. And Jupiter has such a strong influence on the asteroid belt that it does these resonances. And I talked about that with Mercury. But Jupiter pulls on the asteroid belt continuously. So as asteroids are wrapping around the sun, this is the sun, and they're wrapping around. As they're going around the sun, and let's say Jupiter is my little poster out there, okay, with the big moon on it. As the asteroid belt is it's coming around, and then it goes around this way, and then it meets in line between this and the poster. So it's right in the middle. Jupiter is so strong it will start pulling it towards it. But this only happens in certain places. So maybe I believe it's like 3-to-1. So it's like 3 orbits. It will pull it away. So that's one. And then there's a 5-to-2 ratio, a 7-to-3, and then a 2-to-1. And those areas are called Kirkwood gaps because Kirkwood, who was an astronomer, figured out that there are these gaps in the asteroid belt where there's nothing because Jupiter likes the resonance integers and will pull it away. So that's why we have that. In the Kirkwood gaps, there's like specific areas of asteroids where they like to conglomerate. There's like, oh my God, where are all of them? I know the Trojans are one of them. And there are some other ones as well. I think the Spartans are one of them. Trojans, again, it's all Greek themed. And then you can get meteors from there. Meteors are rocks that streak the sky, so they can be shooting stars. They're just hot rocks that come from the atmosphere. And then we have meteoroids, which are a debris in the solar system. And then we have meteorites, which are the ones that actually hit Earth from space. So that's the difference. And also about meteors too, is when Earth is orbiting and there's a cloud of dust in our orbit and Earth passes through it and kind of knocks into it. That's when we get meteor showers because all of that dust is falling onto Earth and we see a bunch of streaks. So when we go through a cloud of dust, we get that. I think that's all I have to say about the asteroid belt for now. I want to talk a little bit about tides, so I'm going to go to my notes again. I could talk about this for a long time. I'm going to assume most of us already know about like the water cycle and stuff like that, and photosynthesis and fun stuff that happens on Earth. What do I want to talk about? I want to talk about the magnetosphere and tides. I think I'll talk about those. So Earth is really unique in the fact that it protects us from the solar wind and solar radiation using the magnetosphere, which is essentially what it sounds like. It's a giant magnet around Earth generated by our core because it's iron and we spin once a day, and when you get motion in something that's going to have a charge, so metal, you get electricity, and then it creates a magnetic field. And so, yeah. And then we have electric currents in the iron, and then it produces this field. And it kind of looks, I want to show you in my notes here. But this is kind of what it looks like. So this is Earth. And then we get these loops where we get this current that's coming out and back in, out and back in. And it makes this kind of shape. And another interesting thing is the side closer to the sun, this side, is more constrained. It's kind of shortened and smaller, and this side that's farther from the sun is more spread out. So as a wave goes through, it kind of shortens this side. And so that's the magnetosphere. And we call the side that's drawn out the magnetotail. And it basically has particles that are charged from the solar wind that come through, those photons that come through, and it makes the solar wind glow sometimes. These are from CMEs or solar flares, and it shoots a bunch of material out, and sometimes the solar wind gets really strong, and it hits the side that's constrained, breaks those magnetic field lines, and they loop back around. And then so basically, like, if I could simulate it, here's Earth with the shorter side and the tail on the other end. A wave of particles hits it. It basically, like, breaks the magnetic field lines. They loop back around to the magnetotail, and then the energy kind of, like, whips back to Earth, and that's why we see auroras. So they're basically a bunch of charged particles in the atmosphere. Yeah. Okay, another thing. We see auroras all the time. We can see them in the day. There's a bunch of light scattering in the atmosphere called Rayleigh scattering, and we can't really see through that, so we don't see the auroras. But they're called cusp auroras, and they're basically where light comes in through the poles, and it can make like a tiny little circle of aurora called a cusp aurora. I would recommend looking it up if you're interested. But cusp auroras are really cool, and they happen a lot. And yeah. And now we're going to talk about tides. I feel like I want to talk about magnetic pole shift. But maybe I can... Well, okay. Basically, Earth's magnetic pole can shift, but it's kind of unpredictable, and it has to do with that carbon dating under the Atlantic Ocean. And we can't really predict when it's going to shift because it happens sometimes every 10,000 years, and then every, like, 100,000 or million, and then it's like, wait, what? It's not predictable, it's weird. And we're not sure why that is, but that's a magnetic pole shift, basically. And it changes direction every time. So that's fun. We don't know why that is. Yeah. So, let's talk about tides in the moon. The moon is a pretty prominent object, and tides basically happen because the strength of gravity kind of weakens or drops off at the square of what the distance is. So what that means is as you get more distant, gravity drops off faster, essentially. And so the moon is tugging on Earth, but it's not a big enough pull to pull the solid rock, so it pulls the water instead, the oceans. And essentially, as the moon is orbiting around us, the water kind of pulls towards it. So as the moon is going here, it pulls towards it, but remember, Earth is also spinning at the same time. However, the moon goes around the Earth every 27 days or so. And so it's not going around the Earth once per day. So it's going really slow, whereas the Earth is spinning really fast. That's why we see the moon every night, and it's generally in the same location every day. Kind of. Anyway. it moves more slowly relative to Earth. We spin around once a day. And so if we kind of imagine the moon as stationary, just for the purposes of this, if we imagine the moon as stationary, and let's imagine, again, that's the moon, Earth is spinning around once a day relative to the moon. So the moon is pulling equally on all sides of the Earth's oceans at some point in the day. But if my fist is Earth, this side of my fist that's close to the moon is going to have huge tides because the water's pulled towards it. But the side that's away, the water's going to kind of like not be as strong. And so a lot of people think like, wait, but wouldn't all the water be pulled towards the moon and this side have like no water? And the answer is no. What's so interesting about tides is that it essentially makes it so that the shape of the tide is kind of more similar to this. So if this is the moon, it pulls water here, but then this side isn't really affected, so it just stays. It more grabs water from here, which is hard to get your head around. But yeah, so we have high tide 2 times a day and low tide 2 times a day. And then there are different types of tides. So if the, I'll just show you the configuration again. But we can get this really, really high tide if we get the moon and the sun are acting together with their gravity, and we get something really, really interesting there. I forget exactly what that is called. There's a spring tide, and then again, this isn't my area of expertise. I don't remember. But we can get a tidal reduction, and I know that the expansion and reduction is by 25% only. It's not too huge, but this is a recession where the moon and the sun are pulling in different directions, basically. And so that gravity kind of evens out. What else do I have to say? For now, I think that's it. We've gone on for a while, and I know you're probably tired and want to go to sleep. But I'm excited to talk about the Jovian planets, and I hope that I'll be able to soon. So, thank you for listening. I know that I was kind of scattered this video, but I promise when we get to deep space, I will be so excited. But again, it's not, I know some, but I don't know enough details to like speak for 50 minutes without referencing notes for sure. But yeah, if you are interested in hearing about whatever topics, just let me know. I would be happy to include them in a video at some point. And yeah, so if you know any radio astronomers, let me know. I'd love that. So